Besides the Sun, Betelgeuse is the largest star visible in Earth's night sky. It is located in the Orion constellation, and can only be seen from the southern hemisphere. In 2024, scientists observed the surface of this star in detail for the first time, discovering boiling hot plasma forming massive bubbles. This star's radius is nearly 300 times that of the Sun. However, despite Betelgeuse being the largest star in the night sky, it is far from the largest star in the universe. Until recently, the title of the largest star belonged to Uy Scuti. In 2012, astronomers used Chile's Very Large Telescope to measure 3 supergiant stars in the Milky Way's center, including Uy Scuti. Its measured radius was about 1,708 times that of the Sun. But don't think this star is just 1,700 times larger than the Sun. Let me explain what this really means. Imagine you have 2 cubes in front of you. The white cube has a side length equal to the Sun's radius, while the gray cube's side length is twice the Sun's radius. Although the gray cube's side is only twice as long, its volume can contain 8 white cubes. This principle applies to any three-dimensional object, including celestial bodies like stars. This means, if scientists' calculations are correct, Uy Scuti could theoretically contain nearly 5 billion suns. However, the latest measurements in 2023 showed this star's radius is actually only 909 times that of the Sun. So, in 2024, the title of the largest star was given to WOHG64. Its radius is over 1,500 times that of the Sun. This giant star is located in the Large Magellanic Cloud, a neighboring galaxy, about 160,000 light-years from Earth. If we placed it where the Sun is, its size would extend beyond Jupiter's orbit. This star is surrounded by a massive cloud of dust and gas. Intense stellar winds continuously blow this material away. The total mass of this dust cloud is about 9 times that of the Sun, extending over a light-year. In fact, among known stars, one is much larger than WOHG64, the red supergiant Stephenson 2-18. Its radius reaches 2,150 times that of the Sun. But despite its enormous size, scientists remain skeptical about it. The reason is that its existence violates known physical laws. Its radius exceeds the so-called Eddington limit. Typically, a star must maintain hydrostatic equilibrium to avoid being torn apart by internal plasma pressure or collapsing into a white dwarf under its own gravity. This balance determines the relationship between a star's mass, radius, and temperature. But Stephenson 2-18 breaks 2 of these rules. Its radius and temperature exceed theoretical limits. Such stars should have a maximum temperature of around 3,500 Kelvin, but Stephenson 2-18's surface temperature is only 3,200 Kelvin, lower than the coolest known supergiant stars. This suggests either measurement errors or that our understanding of physics is incomplete. Thus, WOHG64 is still considered the largest star in the universe. But in the universe, stars are measured not only by size but also by factors like luminosity and mass in space. For example, stars classified as hypergiants, like our 136A1, have a radius only 42 times that of the Sun, but it is considered the most massive, brightest, and hottest star in the universe. Its mass is nearly 200 times that of the Sun, making it the second most massive known star. But this title may not last long, as massive stars lose material due to intense stellar winds. For our 136A1, the stellar wind speed reaches a staggering 2,600 kilometers per second, causing it to lose over 30 trillion tons of mass per second. Scientists estimate it has already lost about 35 solar masses since its formation. Moreover, its brightness is astonishing, nearly 4.7 million times that of the Sun. If our Sun reached this brightness, Earth's surface temperature would soar to a terrifying 16,200 Kelvin, almost 3 times the Sun's current surface temperature. Even so, its brightness ranks only 7th in the universe. The title of the brightest star belongs to Godzilla in the Sunflower Galaxy, with a brightness 255 million times that of the Sun. It's simply unbelievable. However, in the contest for the hottest star, our 136A1 easily outshines Godzilla. Its surface temperature is about 46,000 Kelvin, 1.5 times that of Godzilla and 8 times that of the Sun. But even so, it cannot compare to the true king of heat. This star, with a radius only half that of the Sun, is WR102. It is one of the most dangerous stars in the universe. Its extreme stellar winds strip away its material at several times the Sun's rate, and its intense ultraviolet radiation compresses and ionizes surrounding interstellar material, forming a bubble-like nebula around the star. All this is due to its extremely high temperature, reaching up to 200,000 Kelvin. If our Sun became this hot, it would not only evaporate Earth's oceans and atmosphere but also vaporize most chemical elements on Earth. Scientists speculate that WR102 is nearing the end of its life and may soon end in a supernova explosion. At that point, its title as the hottest star will also pass to another. In the universe, besides stars thousands of times larger than the Sun, there are also stars famous for being the smallest. For example, the star with a very long name, EBLM J0555-57b, has a radius and mass only 8% of the Sun's. It is the smallest known star capable of sustaining nuclear fusion in its core. Most astonishingly, it is even smaller than Jupiter. So why didn't Jupiter, which is larger, become a star? Although this gas giant's mass is twice that of all other planets in the solar system combined, it is only 1/1000th of the Sun's mass, far too small to trigger nuclear fusion. But not all stars follow this rule. For example, another star with a long name, PSRB 0943+10, is perhaps the most incredible celestial body in the universe. It is a pulsar made of neutrons, with an extremely strong magnetic field, rotating once every 1.1 seconds. Most surprisingly, this pulsar's radius is only 2.6 kilometers, less than 1/4 millionth of the Sun's radius. Despite being so tiny, its radiation could destroy all life on Earth instantly. However, its rotation will gradually slow and eventually stop, and its temperature will continue to decrease, leaving only a dead core. In the Ursa Major constellation in the northern sky, there is a supernova named IPTF-14HLS. In 2014, scientists observed this supernova, over 500 million light-years from Earth, explode. Initially, it appeared to be a typical astronomical event, but the explosion occurred repeatedly. Over the next 1,000 days, scientists observed 5 brightness peaks, each equivalent to a full supernova explosion. Even more puzzling, historical data revealed this star had already exploded 60 years earlier. What is going on? Scientists still have no clear answer. One hypothesis suggests that the star's core may produce antimatter, causing annihilation when it contacts regular matter, triggering supernova-like phenomena. Perhaps future discoveries will unravel this mystery. But one thing is certain, the more we explore the universe, the more record-breaking stars we will find. For example, a type of star called a Thorn-Zitko object, according to scientists' theories, may not just have a compressed helium core but possibly a mature neutron star at its center. Such objects may form from collisions between red giants and neutron stars. This hypothetical star type was proposed in 1977 by physicist Kip Thorne and astrophysicist Anna Zitko. Later, Chile's Very Large Telescope discovered a potential Thorn-Zitko object, named HV 2112. However, for years later, new research disproved the presence of a neutron star inside this red giant, as such objects require high concentrations of elements like rubidium, but detailed observations showed this star's element content didn't meet the required levels. Yet, in the same year, scientists discovered another candidate, HV 11417, though its identity remains unconfirmed. In 2023, the James Webb Space Telescope discovered several dark matter star candidates, named JADES GSC 13-0, JADES GSC 12-0, and JADES GSC 11-0. These objects are extremely distant from Earth, so the light we see now was emitted 13.8 billion years ago, just 200,000 years after the Big Bang. If confirmed, this would be a major breakthrough, as the existence of dark matter remains an unsolved mystery. According to theory, dark matter stars may form from the collapse of hydrogen and helium at protostellar centers. In early universe galaxies, dark matter particles collide and annihilate, triggering chain reactions in gas clouds. These processes heat the gas clouds, ultimately giving birth to stars. Dark matter stars may have temperatures similar to the Sun, but with a mass 1,000,000 times greater and a brightness 1,000,000,000 times that of the Sun theoretically. Such stars collapse into supermassive black holes at the end of their lives. Scientists now need just one key piece of evidence to confirm whether these objects are dark matter stars, such as a breakthrough in the electromagnetic spectrum, like detecting a specific helium isotope. Another unique celestial body in the universe is the black dwarf, the final evolutionary stage of medium-mass stars like the Sun. Scientists have not yet discovered black dwarfs, possibly because the universe is too young. No star has reached this stage. When a Sun-sized star's nuclear reactions cease, it sheds its outer material, forming a nebula, leaving a highly dense white dwarf at its center. Its temperature ranges from 4,000 to 150,000 Kelvin, but since the star's core is dead, it can no longer maintain its temperature. It gradually cools, eventually becoming a cold, dense black dwarf. This cooling process takes about 10 trillion years, while our universe is only 13.8 billion years old. This is why black dwarfs have not yet appeared. Today, we've discussed so many types of extreme stars. So, in your opinion, which one interests you the most? In the vast universe, countless surprises await our exploration and discovery.